Good morning. Welcome. And welcome back to those of you who've been here throughout the series. If you have been here throughout the series, you have seen NASA's plans for the next 30 years or so. And the question is, do we have to kill you now? And, the answer is no. This is the civilian space program, and we work for you. So you've seen the plan, and for the last 2 weeks, you've actually seen the program that's underway today to build the transportation system to take people into deep space. Today and next week, we're going to concentrate on two major problems that are between us and being able to execute that plan you saw the first week of going to Mars with people. And Jeff Harris is here this morning to tell you about the problem of landing people on the surface of Mars and how we go from interplanetary speeds down to 0 miles per hour safely. And last week we talked about the rocket and how the rocket accelerates the people, the astronauts and their cargo out of the gravity well that we live in, this steep energy well that we live at the bottom of. Now that once the astronauts are in space, it's very easy to move around. Okay, the only force you have to overcome there is inertia, and but the problem is when you get to the next destination, you've got to take all that energy the rocket put into you. So now you're speeding along at 25,000 miles per hour, and you got to slow down. So now you're going down the well, and you've got to go down that slope, that energy slope safely. And that's what you're going to hear about today. As you know, at this point in time, we have ideas about how to do that, but we can't say we've got the solution in hand. With that, I'm going to turn it over to Jeff Harris, who is the product line lead at Langley for entry, descent, and landing.
Good morning. Yes. That's fine, yes. Well, good morning, everybody. I'm Jeff Harris. I work here locally at NASA Langley Research Center. And today I get to talk with you about Mars and the challenges of safely and affordably getting humans to the surface of Mars. So first I want to start with an image. Does anybody see anything there that you recognize? Yell it out. All right, so you got the moon. And if you can see a little bit further down, there's this tiny little red dot. That is what Mars looks like in our night sky from here at Earth. And in fact, from the earliest days when humans could first look at the skies, they noticed this strange red light that moved a little differently than the other stars. And so we've been looking at Mars and wondering about Mars for an awful long time. And as we move forward, we developed new technologies such as telescopes, and we're able to look at and see Mars in a lot more detail. And in fact, over time, if you look at the history of observing Mars, you have people in the 1600s able to determine that Mars had polar ice caps. You had also those early observations, they were able to determine the inclination of Mars, or the tilt of its rotation. And then you get into the 1800s, in the late 1800s, and they could see more surface features. And they determined that these were canals that were built by an intelligent species on a dying world. And that was in 1894. This was the thinking at the time. Now, of course, now we know that that's not actually the case. But Mars really is a very interesting place to study. So Mars is the fourth rock from our sun and is named after the Roman god of war. Mars is half the diameter of Earth, but twice the diameter of Earth's moon. And in fact, if you look at the land mass of Earth, took out all the oceans, it's about the same size as Mars. And like Earth, Mars has seasons. It has polar ice caps, it has volcanoes, has canyons, has deserts, and weather. And some of the things on this chart, like I mentioned the inclination in that last slide, Mars's inclination on its rotational axis is 25 degrees, very similar to Earth's at 23 degrees. Its day, the speed that it rotates, at Earth, we're 24 hours. At Mars, it's only 40 minutes longer at 24 hours and 40 minutes. Now, The gravity on Mars is a lot less. It's a smaller planet. So if you weigh 100 pounds here on Earth, you're going to weigh 38 pounds on Mars, which sounds really good to people like me. Yes. So, and the other thing is Mars is further away from the sun. And so only about 44% of the energy that solar energy that reaches Earth reaches the surface of Mars. And then the next big thing would be its atmosphere. It's got very little atmosphere compared to Earth. It's about 1%. And the composition of that atmosphere is quite different. About 95% of its atmosphere is carbon dioxide, where here on Earth that's a very small percentage. On Earth we have a much higher percentage of nitrogen and oxygen that makes up our air. Now the average temperature of Mars is minus 64 degrees Fahrenheit, so it's kind of chilly. But the ranges are, if you go from night, at negative 200 degrees Fahrenheit, but then in the hottest days at the equator, it can actually get up to 80 degrees Fahrenheit on the surface. And as I mentioned, Mars' atmosphere is really thin. In fact, it's too thin for liquid water to survive on the surface. It sublimates directly to a gas. So, but however, several Mars missions have found evidence of past water in the Mars icy soil and in its thin clouds, and we'll talk a little bit more about that. So why Mars? Well, Mars is the most Earth-like of the planets in our solar system. And so by studying these different areas, we're looking at the history of the climate, looking at its geology, we're looking at whether life could have or ever did arise on Mars, and then also evaluating it for the potential for human exploration. So these are some of the key areas that we're really interested in looking at Mars for. And there's one thing that ties all those together, and that's water, understanding the water on Mars. And that is why when we, in the Mars exploration program, when we reinvigorated that in 1996 with the Mars Pathfinder mission, the strategy has been to follow the water and understand the role of water. And we've sent several missions there. And in fact, I'll show you a couple highlights of those here in just a minute. And so the Mars exploration program is moving from follow the water into looking for the signs of life and looking for the possibility of human exploration of Mars. So a few highlights of our relatively recent explorations of Mars. So if we go back to the Mars exploration rovers, these were the rovers Spirit and Opportunity. They were sent there. One of their main questions was to answer, was there water on Mars? And they definitely answered that. Mars was once soaked in water. In fact, in this slide, what I'm showing here, these are perchlorate salts that it found that can only form in the presence of liquid water. And in fact, these particular type were nicknamed blueberries just because of their shapes. But the Mars exploration rovers found 7 different types of formations, types of minerals that could only form in the presence of significant liquid water. So then we move on to our Mars Reconnaissance Orbiter mission. This particular mission had a ground-penetrating radar as well as a very high-resolution camera on it. So what we were able to do with that ground-penetrating radar, if you look at this, is a global map of Mars, and we're looking at the concentrations of H2O, or water, within the relative, about 1 meter up to 2 meters within the surface of Mars. And as you go from the yellows into the blues and indigos, it's higher and higher water concentration. And so what we proved with the Mars Reconnaissance Orbiter is that there is significant water on Mars, particularly toward the polar regions, but there is significant water. What we didn't know is how that exists on Mars. Is it large chunks of ice under the surface? Is it actually, could be lakes under the surface? Or is it just loosely distributed all through the soil or in different types of minerals? So from our remote sensing, we couldn't tell that. We just knew that there was a significant amount of the element H2O underneath the surface. And in fact, the estimates are, if you brought all of that water to the surface, it would cover the surface of Mars about 6 feet deep, the entire surface. So it's a significant amount of water. So what we did then is we took the Phoenix lander. So now we knew there was water there, but we didn't know, as I mentioned, what form it was in. So we launched Phoenix and set that to Mars and landed it in the polar region. And one of the things we noticed right away, from one of the first images back right after landing, this is underneath the lander, you'll see that the landing rocket sort of cleared away an area, and there's this nice, shiny, smooth surface there. So is that ice? What is that, you know? So we took the arm, which has a shovel on the end of it, out right beside the lander and dug just a couple inches in. And so what you see here, this white area, is actually frozen carbon dioxide, or dry ice. Now remember, Mars has a lot of carbon dioxide, so there is an awful lot of dry ice on Mars. But what we also found, which is hard to see in this bottom left corner, it's blowing up there, are these other little chunks. And then within a few hours of that, they actually disappeared. So the water sublimated, right? So we dug later, brought those up into our ovens and our sensors, and were able to prove that that was water ice, very easy to get to within the surface of Mars. So there is significant water on Mars. It exists as ice within the soil, as well as potentially deeper down. It could be liquid water. We don't know that yet. But there is significant water on Mars. As I mentioned, what's the next decade? So we're moving from follow the water to looking for the signs of life. And that's what our latest mission that you may have heard of, the Mars Science Laboratory, is part of that transition. With the Mars Science Laboratory, we landed the Curiosity rover there about 2 years ago, and it's beginning this work of looking for the signs of life. Now, the most important discovery by Curiosity so far is that ancient Mars did have environments that could have supported life. If life had arisen on Mars, there are environments there as that life as we know it here on Earth could have survived. So it looked at the concentrations of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. They're all there in the right concentrations. They also looked at the mineralogy and the clays that were formed in that area, and found that there was significant fresh water, actually, not very salty water at all. And in fact, they believe if we had been there, we could have dipped a cup in the water and drank it without any issue. And so Mars did have habitable environments. We do not know, to be clear, we do not know if life ever arose or currently may exist on Mars. But we do know that there used to be environments where it could have. All right. So Curiosity is really the monster truck of rovers. If you look here, these are the rovers that we've sent to Mars. Our very first one here with Pathfinder, and then the Mars Exploration rovers, and then the Mars Science Laboratory at about 1 metric ton. And that 1 metric ton represents the limits of our current entry, descent, and landing capabilities. So this rover is the biggest thing that we know currently how to put down on the surface of Mars. And that's based on significant technology investments that were made in the 60s and the 70s leading up to the Viking missions and the Viking program. We humans have sent 40 missions to the surface of Mars from Earth. Many of those have failed. It's a very hard place to go, and in fact, if you're keeping score, we've had 16 successful missions versus 24 failures from Earth. But since we're talking about landers today, we've had 7 successful landers, and we've had 8 that have failed. So let's start talking about what it takes first to how do we get to Mars. Now, you all had a presentation on the Space Launch System, I believe it was last week. And so the first thing you need, and we won't go into detail because you already learned about that, is a big rocket, right? And this is the SLS, and it begins with a 70 metric ton capability and will grow to 130 metric ton launch capability. And so let's talk a little bit about how the launch affects entry, descent, and landing. So with your big rocket that leaves, you have to package your payload up on the top of this rocket inside of a fairing. Now that fairing size is limited by what the rocket can launch and the aerodynamic loads that are going to be on it. And its purpose is to protect your payload, whatever we're wanting to send to Mars, from the atmosphere of Earth as we're trying to push through it really quickly. But the size of that fairing limits the size or the diameter of the vehicle that we can send to Mars. And so why is that important to entry, descent, and landing? Well, the larger diameter vehicle that we can get to Mars, the more drag we can create as we're trying to enter that atmosphere and slow down, and therefore more mass we can get to the surface of Mars. But right now, with our current limitations, as I mentioned before, we're limited to about 1 metric ton to the surface of Mars. So with that fairing up there, we have our vehicle packaged in it, we launch, we accelerate. After we get out of Earth's atmosphere, we drop the fairing, we now get up into orbit, we check our orbit, and then we ignite the engine again to accelerate ourselves to escape velocity and get us on the right trajectory headed to Mars. And that's when we move from the leaving Earth into what we call the cruise phase. So we go from launch and departure to the cruise phase. And the cruise is where we are traveling from the Earth vicinity to the Mars vicinity. And now I have a short video here that describes how we do that.
How do you get to Mars? If you want to send a spacecraft all the way to Mars, first you'll need a fast rocket to escape the pull of Earth's gravity. The heavier your spacecraft, the more powerful your rocket needs to be to lift off. Next, make sure you launch at the right time. Mars and Earth orbit the Sun at different speeds and distances. Sometimes they're really far apart, and other times they come closer together. About every 2 years, the two planets are in perfect positions to get to Mars with the least amount of rocket fuel. That's important. The total trip is over 300 million miles. Finally, make sure your aim is right. You can't shoot for where Mars is at launch time. You have to aim for where it will be when you get there. It's a lot like how a quarterback passes a football. Also, you may need a few thrusts to correct your direction along the way so you don't miss Mars. If all goes well, you'll get to the red planet in about 7 or 8 months.
So here we are. We've gone from Earth to Mars. We've arrived at Mars, and this is what the planet looks like as we get there, and we're getting ready for entry, descent, and landing. Now, one thing I'll mention from the cruise, a lot of people, the analogy for that is getting as accurately as we need to Mars is like making a basketball shot from New York to Los Angeles. Now, as it said in that video, we're able to cheat a little bit because we can make small corrections on the way there. But we have to get a very accurate departure from Earth, and we've been able to do that very well the last several missions. And so that is working really well. So here we've arrived at Mars. This is what it looks like as we're starting to get pulled into Mars' gravity well. It's accelerating the vehicle toward Mars. And so we're ready to start entry, descent, and landing. But what really is entry, descent, and landing? And so entry, descent, and landing is about the controlled flight of the vehicle system through all appreciable atmospheres, including the safe landing where that's applicable. And so we have to get from here, where in this case relative to Mars, we're going about 13,000 miles an hour, down to the surface. And in this case, I'll show you what the target was, the Gale crater. This was our landing site for MSL and what it looked like as we arrived at Mars. And we have to get from that 13,000 miles an hour down through the atmosphere to the surface to roughly 0 miles an hour for a nice soft touchdown. That's what you want. Once you've committed to EDL, you're going to touch down. Now, hopefully we don't make another crater, but we want to touch down nice and softly. So let's talk about what the key challenges are for doing that. The first is at Mars, there's too much atmosphere to land like we do on the moon. So what that means is we're traveling so fast, and as we start interacting with this atmosphere that's there, there is an awful lot of force on the vehicle. There's an awful lot of heating on the vehicle. And the atmosphere itself has different winds, has density variations. And so all of these things conspire so that we can't just do a propulsive descent like we do at the moon. We actually have to use the atmosphere. The next is that there's too little atmosphere to do it the same way we do at Earth. There's only about 1% of Earth's atmosphere at Mars. And so that would be kind of like landing the space shuttle at 100,000 feet here at Earth. There's just not enough atmosphere to do it that same way. Some of the other challenges are there is a wide variety of terrain elevations as well as the types of terrain to deal with when we get to the surface. And then we have this issue of we design an EDL system or an entry, descent, and landing system here at Earth, but we don't have good ways to test that end to end here at Earth, to test the entire system. And it has to be done at Mars. And so that's a huge challenge for getting a system that will be reliable and actually work when we get to Mars. So first, let's talk about the atmosphere. Like I said, it's a very dynamic atmosphere, and it's poorly characterized to date. Now, there are no large storm systems like we have here at Earth, but the seasonal and the diurnal variations are actually larger than what we see on Earth. And there are large, sometimes global dust storms, and that has huge changes on the density of the atmosphere and changes how we fly through it. And actually on Mars, there are even dust devils. So in this case, you know, the sun can heat the Martian surface and create winds, and sometimes those winds create dust devils. This particular one was captured by the HiRISE camera on the Mars Reconnaissance Orbiter, and then we created a three-dimensional model of it so that we can kind of fly around it, kind of like you're in a helicopter. And what you can see here, this dark line on the surface, is actually the shadow of the dust devil, which allowed us to recreate its height. And so what you're able to see from MRO, we'll go back to the original image, is that the dust devil is about 100 feet wide on the surface and about a half a mile tall, so it's quite a large one. But one of the things we didn't know before sending the Mars exploration rovers is how prevalent or how common dust devils are on the surface. I don't know if you all remember, but those exploration rovers, when we sent them, were only designed for a 90-day life, because one of the main reasons is we thought that dust would collect on the solar cells and they wouldn't be getting enough energy to keep themselves warm and their electronics would fail. Turns out, dust devils are pretty common. So you can watch their battery life going down, 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 and then it gets hit by a dust devil and cleans off the solar cells, pops back up. So we've had these exploration rovers up there for many, many years. In fact, they had their 10-year anniversary. One of them is no longer operating, but the opportunity is actually still operating on the surface. So the point is that the vehicle system that we're trying to get to the surface of Mars has to contend with a lot of atmospheric variability. So now let's talk about the terrain elevations. This is a global map of Mars again. And what we're showing here, the black areas are the parts of Mars that are above 2.5 kilometers in altitude. And so this is the type of access that we'd like to have to Mars. We'd like to be able to land anywhere the colors are on this map. And what you see here, the red X's, are where we have landed. And so if we now look where those actually are, those have actually been all very low altitudes. With our current technologies and our current entry, descent, and landing techniques, we have to land very low, at very low altitudes, so we have as much atmosphere as possible to work with, to slow the vehicle down and get it safely to the surface. And so this is one of our big challenges. So there are also different types of terrain hazards. Listed here, you got mountains, craters, canyons, rocks, right? But the point is, we do know a lot more now than we used to. So if you look here, in the Viking era, at the same scale, we really couldn't tell anything about the surface. And then the Mars Global Surveyor camera, hey, we could see, hey, there's actually a crater there, but can't tell much more. And these days, now with our higher resolution camera on Mars Reconnaissance Orbiter, we start being able to pick out features and terrain types and understand better where we're actually sending these vehicle systems and can better prepare them for where they have to land. I mentioned the EDL system verification problem. So it's really because of the complexity and the environments that we're sending it to, the EDL systems for Mars generally can't be tested as flown here at Earth, as we intend to fly them here at Earth. So we do component tests here at Earth to build models of how the different pieces of the entry, descent, and landing system work. And then we assemble those models into an end-to-end simulation. And so all of the models of the EDL component subsystems are brought together into this end-to-end system simulation. So you have models of the vehicle mass properties. You have models of the atmosphere that we've been talking about. You have models of the parachute to understand the dynamics when that deploys. You even get into the physics-based modeling of the radar system to understand what kind of signals you're going to get back from wind and how much dust and material is going to be kicked up as you get close and how the radar will react to that. So there are a lot of different models that get pulled into this. And the simulation exercises both the flight vehicle and the algorithms that autonomously fly the vehicle in the virtual environment. And that's one of the things that actually these simulations are very good at. We can push the system beyond even what we're intending it to fly through. We can find its sensitivity. So we disperse different variables, such as how well we know the vehicle's center of gravity or how much wind it might encounter. And that way we can understand better how this system will perform when it actually gets there. Now we run literally hundreds of millions of these entry, descent, and landing runs in computer simulations in the development and the verification of these EDL systems. And actually now these systems are so complex that the only complete system performance verification are these end-to-end simulations. So let's take a quick look at what the entry, descent, and landing sequence at Mars looks like. All right, so we arrive at Mars, and we've had a cruise stage, which is that little thing up on the top there, attached to us and helping us get from Earth to Mars accurately. Well, we jettison that, and then we turn the vehicle to face the Mars atmosphere at the angle that we want it to hit the atmosphere. And then, in this case, I'm showing the Mars Science Laboratory sequence. We jettison a balance mass. This is important because we now have changed the balance of the vehicle, and we do that on purpose so that when we start flying through the atmosphere, the vehicle won't just fly straight in like a bullet. It'll fly at an angle of attack. It'll fly at a slight angle, and that gives us a lift vector. And so we can use that lift vector to then control and steer the vehicle and help us slow down more. And I'll talk about that some more in a little bit. So we've jettisoned that balance mass. Then we come slamming into the atmosphere at about 13,000 miles an hour. It starts heating. So that heat shield, the rigid heat shield up front is protecting us from that. It gets up to about 3,800 degrees. And then we continue going through that peak heating. And then we reach peak deceleration, which for MSL was about 10 Gs. So now think about that in regards to humans. Right? We can't subject our humans, particularly after being in space for a long time, to 10 Gs. So we're going to have to, for humans, slow down a lot earlier and slower, right? But for our current state of the art, it's experiencing 10 Gs, and then we start maneuvering, essentially doing S-turns in the atmosphere to help us slow down. And as we get down closer to Mach 2, we can deploy the supersonic parachute, which helps us slow down a lot more. We drop the heat shield. The radar system then is looking for the surface to find out exactly how high we are and how fast we're moving. And once it finds that, it drops our payload. In this case, for this mission, it was the rover with a rocket pack, actually, called the Powered Descent Vehicle. And it continues slowing down relative to the surface and touches down. So that is the current state of the art for entry, descent, and landing at Mars. And I'll show you a little bit more about that in a few minutes. But while flying through the EDL sequence, the vehicle system needs to be able to land within a defined area. Now, I showed you what Gale Crater looked like from orbit before. Here's a close-up of it. So this was the landing area for that Mars Science Laboratory mission. And we targeted Gale Crater. But that was impossible just a few years ago because, when we did the Pathfinder mission, its landing uncertainty was larger than the crater itself, right? But we've gotten a lot better since then. And so here's the landing ellipse, or the landing uncertainty, as we call it, for the Mars Science Laboratory mission. So after all the calculations we do and understanding how this EDL system will perform, we're very confident it'll land somewhere in that ellipse. The target, of course, is the center. And in this case, for MSL, we actually did pretty well. We were only about 2 kilometers away from the very center of that ellipse. But the point is, for humans, we need to be able to land in an area that's 10 times smaller than that even. So within about 0.1 kilometers of our targeted landing area. So let's take a quick look at how the history of entry, descent, and landing at Mars. I mentioned the Viking mission. So Viking sent 2 probes to Mars. They were landers. They entered with a rigid 70-degree sphere cone aeroshell and went and had a supersonic parachute to a propulsive descent on the surface. Now, this was all possible. This was the first landings at Mars, right? So this was all possible because of the significant technology development activities we had in the 60s and 70s. Those activities made it possible for us to understand the 70-degree sphere cone aeroshell and how that was going to fly. It qualified this disk gap band supersonic parachute so that we would be able to use that, as well as the autonomous propulsive landing. So if we look at some of the more recent missions, Mars Pathfinder, it landed a small rover there, used airbags, and I'll show you that in just a second. Mars Polar Lander was another lander sort of like the Viking Air, but we lost that one. We don't know exactly why, but through the mishap investigation, the most likely scenario was that its computer was listening to its touchdown sensor too early. So this touchdown sensor is looking for a shock to hit when it touches down on the surface to turn off its landing engines. And so what most likely happened is it's listening to that too early, and then it deployed its landing legs, boom, and shocked the system, and the little sensor thought it had touched down, it turned off the engines, and most likely fell the last 60 meters to the surface. So we then did the Mars exploration rovers, and so let's take a look at their EDL architecture. So again, we have the 70-degree sphere cone aeroshell. We separate from the cruise stage, and we're coming straight in or ballistically, into the Mars atmosphere. So that heat shield protecting us from the air heating. And we're going through peak heating and now peak deceleration. And as we get down closer to Mach 2, we can deploy that supersonic parachute. And now we're still flying relatively horizontally at this point, but the parachute, that's loud. The parachute is actually working on slowing us down and sort of tipping us over, and then we can drop the heat shield, right? And then here's where it's different than what we saw before. It has the payload in this tetrahedron hanging down below, and that tetrahedron has airbags all around it, which will inflate as we get a little closer to the surface. And so those are just like airbags for your crashing, right? So, and as we get within about 30 meters of the surface, these retro rockets fire, bring the entire system close to 0 miles per hour relative to the surface, and then drops it. And that system, that airbag system, hits the surface at about 54 miles an hour, and then bounces along until it stops. Now in the actual missions, this is a simulation, but in the actual missions, they bounced about 30 times before they stopped. And then it deflates the airbags, and then opens the tetrahedron, and you have your payload safely on the surface of Mars. In that case, it was one of the exploration rovers. Yes?
What are you using at the moment as a heat shield? Is it similar to the old Apollo?
So similar, in that it's a rigid heat shield. The material, the actual thermal protection system on the latest ones is called Pica, and that's different. For the Apollo ones, it was called Avcoat. So it's a different material, but the same type of idea with that rigid aeroshell and creating the shock in front of the vehicle to carry a lot of the, it ablates. It's an ablative, is what it's called. You burn off part of the heat shield material, exactly. Yes?
How do you avoid landing on a very steep hill?
The question was, how do you avoid landing on a steep hill or incline? And so one is we characterize how well the system can do that. Like what type of incline could it withstand, right? And then we've used our current orbital assets there to create what are called digital elevation maps of the area that we're going to land, a wide area. And so we understand where these keep out zones are, and so we define our landing ellipse away from all of those bad areas. Yep. Yes?
What's the composition of those balloons after demise or impact?
So the balloons were a composite material. It was based on a Kevlar based, and then it had essentially a gas barrier on the inside to allow it to inflate. But they had a very tough exterior that I believe was Kevlar based. Yeah, and so we did an awful lot of testing of those, dropping them on sharp rocks and throwing them sideways at things to make sure that they wouldn't rupture within the parameters of what we were or how we were landing. Exactly.
What's the size of the landing area that you're looking at dimensions for humans?
For humans to Mars, we need to be within about a 100-meter ellipse, or 0.1 kilometers. Right now, we've got about depending on lots of things, it's between a 5 and 10 kilometer ellipse that we can land in. So we're over an order of magnitude away from where we need to be in our landing accuracy. So then I mentioned the Phoenix mission before, and so this is now a modern lander, but still in the same type of architecture that we did for Viking. So 70-degree sphere cone, getting through the heating, same type of supersonic parachute, going to a propulsive descent and landing, which was successful. And so now the most recent one we have is the Mars Science Laboratory, which was landing the Curiosity rover on the surface of Mars. So this represents the state of the art, so we'll watch how we got to the surface with MSL. So again, same type, but much larger, same type of rigid aeroshell. We'll drop the cruise stage. We now reorient this entry vehicle toward the atmosphere of Mars. We drop that balance mass, remember, so we offset, so we'll fly at an angle of attack. And so now we start to get into the sensible atmosphere. All right, so the vehicle starts to feel deceleration. It uses rockets called a reaction control system to keep itself oriented correctly. And then here, you can see we've gone through peak heating and it's starting to steer back and forth in these S-turns, continuing to slow down. It gets through peak deceleration, which again for MSL was about 10 Gs. so now we're continuing to slow down, and as we get close to 2, we kick off more mass to recenter ourselves. We don't want to be offset anymore, so we can safely deploy the parachute. Which, there's that supersonic parachute again, the same style, disc gap band that we used for Viking, but much larger. So now we drop the heat shield, and the radar's looking for the surface. And once it finds the surface in a solution, it's going to drop the rover and the powered descent vehicle, which is the rover's rocket pack. They fire and continue decelerating the rover relative to the surface. And one of the first things it does, though, is a big left turn to get away from the parachute. So it's the parachute avoidance maneuver. And so it's moved away from the parachute. Now there's radar system up front there. It's continuing to look at the surface and understand how our altitude and our velocity relative to the surface. And as we get closer, there's an instrument called the MARTI instrument. It's a camera right here that's also looking at the surface and comparing features to understand how much we're moving side to side. That's what it's doing there. And so now as we get closer to the surface, we lower the rover on the tether system below this rocket pack, and it continues decelerating very slowly toward the surface now, and the rover has set its wheels into a landing configuration. And right now, everything's just waiting for the touchdown sensor, and once it senses touchdown, it cuts those tethers, and the powered descent vehicle flies away to a safe distance and crashes, but a safe distance away from the rover. And one of the big benefits of landing this way is you've now got your rover system on the surface essentially ready to go. All it has to do is stand up its remote sensing mast, and it's essentially ready to go. As opposed to, what I'm relating that to is the Mars exploration rovers that were packed in that airbag tetrahedron. They were folded up like origami, and it actually was, I think it was almost 3 weeks of operations to unfold everything and get them set up and actually ready to operate. And so here, we've landed within our landing ellipse, and there in the back is called Mount Sharp. It's the center of that Gale crater that we talked about. And it has been operating for just over 2 years and has just now gotten over to the base of Mount Sharp. Now, it's done an awful lot of science on the way there. We've learned that there were small rivers that even at least knee deep in that particular area. And I mentioned the big discovery for MSL is the existence of ancient habitats that could have supported life. So it's done a lot. But the point is that this is the limit of what we can currently do with our current entry-descent landing technologies. And so we have a significant technology gap. Look just along the bottom here. This is too many words on this slide, but where we are currently is able to put 1 metric ton within about a 10-kilometer ellipse and access about 40% of Mars' surface. And so where we need to be, potentially, for human missions is able to land 40 metric tons within a 1/10 of a kilometer of our target and have nearly global access. And so it is a huge challenge. It's why EDL at Mars is considered one of the 2 biggest challenges for human exploration of Mars. The other one being radiation protection, which you'll hear more about next week, I believe. But NASA has set the goal of having humans at Mars in the 2030s. And to accomplish that, we're going to have to leverage activities all around. It's a very success-oriented goal to be able to do that within 20 years. Most entry-descent landing capability roadmaps show you have to have a consistent effort over 20 years for us to be able to get there. And so we're going to be leveraging our international partners and commercial partners to get there. Other missions within NASA that aren't just the human exploration portion of things, like our science mission directorate and the missions that they send to various planets. All of these things are going to need to combine to help move us stepwise closer to humans on Mars.
Question.
Yes?
During the heat shield burn to Mars, does mission control lose radio control completely?
Okay, yeah.
Like on Earth?
So the question is, during the entry, when the very high heating portion of entry, does mission control lose the radio contact with the vehicle? Control is what you're saying. So first of all, communication time-wise, we're about 14 minutes away. So the vehicle is actually working autonomously that whole time. There's not any active control. So from the time we've started entry at Mars, right, so when we get that signal, 14 minutes has gone by from the time when it actually started entering. And so it's either safely on the surface or crashed by the point we get that signal that it started, right? So, but what does happen during that entry, there is some radio blackout, and there are special radios we use that are very small data pipes that send us some very small amounts of data all during that time. And so it's all about the health of the vehicle, and if we have a bad day, helping us understand what happened.
What causes the radio blackout?
So that has, well, yes, the question was what causes the radio blackout? It's the ionized flow. So we're slamming into this atmosphere, and we're hitting it so hard that we're disassociating the species and creating ions, heavy ions, and a plasma flow. And so that then surrounds the vehicle, and the radio waves can't get through, right? Yes?
Is the United States the only terrestrial nation which has landed Mars?
So the question is the United States the only nation that has actually put landers on the surface of Mars? We're the only ones that have done it successfully. So there have been Russian landers. The closest one, they believe they got a signal that it had landed, but they lost contact immediately, so we're not quite sure. Most of the others failed during launch or failed during EDL. And there have been European smart landers that also failed during the attempt. So the US, so far, is the only one that has successfully landed on Mars.
Are these coordinated with other countries?
So are the missions coordinated with other countries? Yes, in that even on like MSL here as an example, there are contributed instruments on the mission from other countries like France and the European Union. Yep, absolutely. Thank you. So landing at Mars is not easy. As we just said, we've landed a total of 7 times successfully on the surface of Mars. And the point is all of these successful landing systems have landed at low elevations, at -1 kilometer or lower. We've landed less than 1 metric ton. And there's been relatively large uncertainties on our landing location. And the EDL system is so critical to the overall mission that it generally drives the mission architecture. And as I've mentioned, all of the current Mars missions have relied on the technology investments in the 60s and 70s. And we've essentially gotten to the end of where we can stretch those technologies, where we can go. So there's going to need to be systemic new investments in new atmospheric flight systems that are the basis for these entry, descent, and landing systems, because that really is the core of EDL, is being able to fly these vehicles through an atmosphere. So the agency has started working on some technologies. Remember we mentioned in the beginning that we don't have the answer right now. I'll talk about some of the things that we're working on. So we've developed new thermal protection systems. These are the materials on the front of the vehicle that protect you from all that high heating. We've got some new deployable aeroshell concepts that we're working on and developing. There are mechanical deployables, and there are inflatable aeroshels. Now remember the inflatable aeroshels. I'll talk about those in more detail here in just a few minutes. And then we have what are called the mid-L over D, or that's mid-lift over drag vehicles. These are more like flying cylinders into the atmosphere. And then we're also developed new parachutes, new supersonic deceleration systems. These systems actually inflate inside the atmosphere and create more drag. And we're also working on supersonic retropropulsion. And this is essentially you're in a supersonic flow and you're going to fire a rocket into that and help yourself slow down. And so that is another key one. And then, of course, the landing systems, from propulsive systems to airbags to crushable structures, being able to actually safely set down on the surface. So how do we put these technologies together for humans to actually get to and explore the surface of Mars? So NASA has done a lot of studies. This I'm not expecting to go through in detail, but this is looking at different combinations of these technologies, and we're running simulations to understand how those might work and which ones are more effective. And one of the key figures of merit is the arrival mass at Mars. How much stuff do you have to get from Earth to Mars for this type of system to work? And this study was done around getting a 40 metric ton payload to the surface. And so in comparing this, we end up actually with architecture number 2 winning out. It had a very low mass at Mars, so around 84 metric tons. But you'll notice that there is one over there, number 8, that's a little bit less in mass, but its EDL sequence has many more critical events, and it's a little more risky. And so we end up saying that architecture 2 is a better way to go. And so that's the thing. If we were to pick today how we were going to get humans to the surface of Mars, this is the architecture we would take, which is using an inflatable aeroshell. I'll talk about those in just a minute. Using an aero capture approach. Again, this is using the Martian atmosphere to help yourself get into orbit. I'll talk about that as well. And then transitioning to supersonic retropropulsion and final autonomous propulsive touchdown as well. So looking at this architecture, we don't see any cliffs. We see that it can scale to the human class missions. Now there's a lot of work to get there, but there's nothing that says that it can't be done. So let's talk about some of those technologies. I mentioned aero capture. So this is when the vehicle system uses active control to autonomously guide itself into, in this case, the Martian atmosphere, flying through the atmosphere, taking a lot of energy out and slowing down, but then fly back out of the atmosphere into orbit. So you didn't have to carry a bunch of rocket fuel to slow yourself down. You use the atmosphere. And this allows you to use smaller, more affordable launch vehicles to get the system there. It also allows you to have a higher payload fraction, meaning since you don't have all that propulsion or propulsive capability that you brought with you, you can have more payload. And the example here, if you're really using air capture, you can have 80% of your vehicle system be your payload, as opposed to if you're doing propulsive, it's about 20%. So it makes a big difference in the architecture studies. So we need to slow down more mass at higher altitudes, we've talked about, right? So the limit of that fairing size for the size of the aeroshell that we can bring to Mars and help us slow down is a big limit. And I just have a small image here on that, but this is supposed to represent the rocket fairing, and then that was the MSL shape, and it was as big as we could make it. But if we used an inflatable approach, which here it is stored, and here it is deployed, we could carry with us, and we stow it and launch it and everything, and then we're able to deploy it or inflate it as we get to Mars, and it's a much larger drag area. So the anatomy of this, you have an inflatable structure. There's two main things. There's an inflatable structure and there's a flexible thermal protection system. The inflatable structure, and both of those, by the way, in this case, are packed very tightly and forward of this, so you have this nice narrow vehicle. All right? So when it inflates, it uses an inflatable torus approach or stacked torus approach, and there's straps that hold together and carry all of the loads. And I don't want you to think, when I say inflatable, I don't want you to think balloon, right? Because a lot of people think of these balloons and they're squishy and stuff like that. This is actually quite a rigid structure once it's inflated, even with just a few PSI differential. And the material is very durable. It's a Xylon-based material, kind of like Kevlar, and it has a gas barrier on the inside. And all of these are made to be high-temperature material systems. And so we have that as the structure. But then when we come slamming into that atmosphere, and we're at 13,000 miles an hour, it's going to get really hot. So we need this flexible, because it's going to be folded up, this flexible thermal protection system to go on the outside of it. And that's what, I guess here, that's a pinkish material along the outside. And that's a material system that can stand up to those really high temperatures. And so if we're able to do this, it allows us to land, if you remember these images, that's our current access. It allows us to be able to land either more mass to the same areas or the same mass to much higher altitudes and have much more access to the surface of Mars. So what I want to show you now is a video of a technology demonstration of this technology. And it's from a mission called IRVI-3, or the Inflatable Reentry Vehicle 3. And it shows the vehicle system. You have the actual video from the test here. This was on the vehicle. And this is an animation showing kind of what it's doing at the time. So we got to about 291 miles high. That's higher than the International Space Station. We then release the heat shield and start inflating it. And you can see it's coming here, and this green line is its full shape. You can see the inflatable toruses and the straps. And then it reorients itself toward the atmosphere of Earth, so that as the Earth's gravity well is now accelerating us and pulling us back down into the atmosphere. There are sensors on the front here to indicate how high the heating gets and things like that, because we're testing this material system. And then we also have a new way of creating a lift vector. This, instead of dropping mass off, we just shift our payload mass within this. And that does the same thing of sort of unbalancing this so that when we fly into the atmosphere, we can get a lift vector. And so here we go into the atmosphere at Mach 10, decelerating and heating, and look at this. I mean, it's flying very steadily. It's hard to even tell that's what's happening over here. It experienced 20 Gs of deceleration because we were trying to really push the system and get as much heating as we could. In a real mission, it would never see actually 20 Gs. But it was a very successful test, and it qualified this particular material system, which we call the Gen 1 material system, to 30 to 40 watts per centimeter squared. And what that means is it would be relevant to the MSL class missions that we're working on right now. But we want this type of system to be able to work for human class missions. And that's the next step that we're working on. We have not done this test yet, but we've started working on it. It's called Thor, the Terrestrial High-Ad Orbital Reentry Test. So we're going to launch on a much bigger rocket and go up higher and faster. We're actually catching a ride with Orbital Science's Antares rocket. And so as they get up into orbit, we'll drop off, and they'll continue on to the International Space Station. But what they've done for us in the partnership is they've gotten our system up to really high velocities and really high energy. And so then we fire our deorbit motors, inflate our new material system. This is now called Gen 2. And we're going to come in with 5 times the heat rate and 50 times the heat load that we did in our previous testing our new material systems. If these prove out, then we're talking about 60 to 80 watts per centimeter squared is what we think this material system can do. Now that starts to become applicable to the human class missions. And that's what we're working for here. The one thing this test doesn't get us is the scale, right? So we're flying a 3.7 meter diameter, and like I said, that would be effective for the MSL class missions. But for human class missions, they're going to need to be 18 to 23 meters in diameter. But we will have proven out the load capability as well as the heat rate capability for this system. So I also mentioned supersonic retropropulsion as being one of the key technologies. So in this case, we're coming in at supersonic speeds, and we need to continue slowing down. And so we're going to fire rockets into that flow and continue slowing down the vehicle. Now, we're partnering with SpaceX on this, and so we have, I'll describe that in a minute. We have computational fluid dynamics to understand how these jets are going to interact with this oncoming flow. We've done wind tunnel tests, and now we're partnering with SpaceX, who is wanting to use supersonic retropropulsion to return its first stage of its rocket as part of their business plan. And so we've partnered with them to get the data from those tests, and we actually have at this point. And so we're starting to use that data to understand what the real next steps should be for developing this technology. Because one of the keys is the particular configuration is very important for supersonic retropropulsion, to understand how you're going to fire these jets to keep your vehicle stable and to slow it down. But again, this is something that is being demonstrated with SpaceX, and then NASA will move it forward on how we need to develop that for human class missions at Mars.
Just a question.
Sir.
You're taking a one-shot approach at this, it appears, with the biggest diameter vehicle to accommodate your load. Could you stack loads within a smaller cylinder and not have to worry about the massive heat load that you're going to put on it as it enters the Mars atmosphere?
So I'm going to try to repeat, make sure I understand. So you're wondering within the launch fairing of our rocket if we can't stack a greater number of smaller loads within that, but using the smaller diameters. Okay, so what we've done is studies based on, look at the different sizes of vehicles that we need, and doing multiple launches or multiple vehicles, looked at in-space assembly of different vehicle systems, and the trades always come back that it's more advantageous to be able to have that larger diameter aeroshell, right? So that's why the high-ad, in this case, the hypersonic inflatable decelerator, gives us so much of an advantage. And did I answer your question?
Oh, it does, but the thing is, if it fails, you're done. I mean, if your one shot goes down and you have a problem with that heat shield coming
Oh, so okay, so it's a reliability, yes, your reliability issue. So yeah, that's what the systems are being designed to be highly reliable, but then I think what you might be getting at is, like with the Viking missions, we sent 2 landers. Even with the Mars exploration rovers, we sent 2 of those, and really, in case one failed, we had another one that was there and ready. And so I can't say for certain that we'll do that with the human missions, but we're going to with the human missions, we make sure the systems are reliable. Most of the landings are without humans. They're going to be pre-positioning resources and getting things, and everything is there and turned on and ready before the humans ever leave Earth. And so if there is a failure, then we wouldn't be sending humans, we'd be sending another mission to pre-position. Yes?
It's asserted that different materials and different gases and different elements are going to behave in a different way in different gravities and different atmospheres. For that inflatable system, typically what gas do you design with to inflate?
Got it. So the question is, for the inflatable heat shield structures, what type of gas do we use to inflate? So in the tests that we've done to date, we've done nitrogen, it's in there, and now for this last test I mentioned, Thor, we're actually going to use Freon, because we're limited in our center body, and Freon is going to be a denser, give us more performance out of our inflation system. So we're going to use the Freon gas there.
Wait a minute, isn't that Freon releasing in the atmosphere is a no-no, and that's why our refrigerator
That is correct. It's a relatively small amount, and we're using it exoatmospherically. But we do. It is what's inflating the structure, and it will come back in. Yeah. Yes.
Right now, you are talking about figuring out how big the transportation system has to be to get somebody on the Mars.
Right.
What the payload can be. But you have to consider that you have to take extra payload up to get it back home.
Yes, exactly. And I'm going to get to that in about a slide or two, I think. Exactly. So the question was that the statement was that we need to take extra payload to Mars to be able to get them back home. And that's absolutely correct. The last thing I want to mention on the EDL technology challenges is being able to precisely land, we mentioned that, but also be able to avoid hazards that we may not have mapped or didn't know about as it's landing. So the first part is precision landing, and that has to do with knowing very accurately where you are, and the vehicle being able to know where it is on a map and accurately navigate to a point. And so our current, this is just representative of our current knowledge of where we are, so that's our error ellipse. But if we, like a certain technology like what's called terrain relative navigation, so a map in the vehicle actually knows the area very well, and it's taking pictures of the surface and can find itself on that map and redirect itself to an accurate point, you then get this tiny little circle of knowledge error of your location. So that's a potential way of getting our landings more accurate. We also have hazard avoidance. So this is using special sensors such as LiDARs and other instruments and cameras during the descent to understand, hey, there may be hazards right where I'm trying to land, and having the ability to divert to a safe site that's still within the requirements of your mission. So now we get to your question about what do we need to take along, right? So if we're looking at the 40 metric ton missions, this would be 2 landers going there for a 40 metric ton mission to Mars. And so the first lander has, the very first thing is the Mars ascent vehicle. So this is how the astronauts would get back off of Mars. It also has the multi-mission surface exploration vehicle. It has a fission surface power unit. It has 2 fetch rovers. It has a drill. And then an ISRU, or in situ resource utilization, so a unit that can actually process the atmosphere and or the ice and water at Mars into usable elements for the mission. And then, of course, there would be a science instrument package as well. And the second lander, bringing the astronauts, would also bring the inflatable habitat as well as a second surface fission power unit and the second Mars surface exploration unit. And so figuring out how to package that and put that all together, right, and get it to Mars. And so here's the current concept, or a current concept, and how we would package that into a lander. And on the bottom, on the base of this lander, is you would have packed away the inflatable aeroshell that we talked about, right? And so the current studies are looking at 40 metric ton missions, as well as 27 metric ton missions and 18 metric ton missions. And that gets to the trades for how many launches you'd want to make. If you could do it with smaller launch vehicles but a larger number of launches, is that better or what? And so those are the trades that are going on now. Yes?
I want the water on the surface of Mars, which is in the form of ice now, to sublimate when you bring it to the surface and you can't use it at all.
Well, so it would, but it's not immediate, right? And we would be storing the water inside of containers, so it wouldn't sublimate from there. But if we just brought liquid water to the surface, yeah, it would evaporate. Exactly right. All right, so this thing, it includes the HIAD system, and then if we're looking at what an entry at Mars might look like with the human class system, we have the inflatable aeroshell with our lander system being protected inside of that, and this inflatable aeroshell would be 18 to 23 meters across, so much wider than the barn here. So it's a very large aeroshell. So the point is, we've seen what we're doing with exploration, and so you've heard about SLS, and we're working with our commercial partners to have access to the ISS as well as to low Earth orbit, and creating that supply line. Whereas the SLS that NASA's going to concentrate on is about getting beyond Earth orbits, or beyond the Earth gravity well. And we're developing that from our initial 70 metric ton capability to the 130 metric ton capability that will carry the spacecraft, the crew, the cargo, the equipment to deep space destinations such as Mars. And really, this is going to be the platform to continue America's tradition of human space flight. Now, in my mind, I believe that we humans can and will get to the surface of Mars. And in fact, remember the picture I showed you in the beginning? It showed what Mars looks like from Earth. Here's what Earth looks like from Mars, taken by one of the rovers. That tiny little speck right there, I blew it up for you, right? So as you're here, so that is everything, everybody that we know, every road, every building, every city, on that tiny little speck. For me, it really puts things into perspective. And so, these are some of the challenges that we're working on today in trying to get humans to the surface of Mars. And I like to think about what's going to be real tomorrow. And so I have a quick little video for you. I'd be happy to take any questions you might have. Yeah, go ahead.
How long can an astronaut stay on the moon before you have to bring him back? And isn't it more economical to have robots doing the job that can stay longer, that can venture further out than the landing site, than having a person there for a very short time and then having to bring him back?
So the question has to do with on Mars or the Moon, because it's like on Mars, yes. So the question has to do with how long astronauts can stay on the surface of Mars versus being able to send robots that can stay there longer. So actually, with the architectures for the human exploration of Mars, they can stay there for quite a long time. And in the initial missions range, we're looking at short duration first, to show that we can get to the surface and get back off successfully. But with the in situ resource utilization, they can actually potentially stay there quite long as we resupply them with a couple main things, but they'll be able to produce their own oxygen and several other the key things that they would need. So we could have long-term stays on Mars, right?
But that would be a long time away from the first missions where you bring people up just for a very short time.
Most likely, but yeah, we're actually trading those things right now. We actually don't know exactly how and when we're going to put humans on Mars and how long we'll have them stay. And part of it does have to do with the orbital mechanics, right? So where Earth and Mars are in relation to each other, if we put them on the surface, and then what it takes to get them back to Earth. So essentially, when we go there and we're going to stay more than just a few days, they're going to be there for almost 2 years. They can be there for 2 years, yeah.
Directly on the first try.
Yeah. Well, we won't do that the first try. We'll actually do it most likely. We'll pretty quickly bring them back the first time. Yeah, hang on 1 second. Oh, there you are. Yeah, go ahead.
I was surprised that you had lift on that inflatable heat shield.
Yes.
Do you absolutely need the lift for control?
So the question is whether we actually need lift with the inflatable heat shields for control. So this is one of the ways that we are looking at controlling it. So we do want lift in some form. We can generate it different ways, but we do want lift so that we can guide these vehicle systems to get them to more accurate landing locations. That's the main reason. So we get a lift vector that we can control. Sure.
Is Langley the lead? Who's the lead center on this PDL? What is Langley's part of it? If you're not the lead center.
Right, so the question is if Langley is the lead center for EDL, and what is our part in it, right? Did I get that right? Okay, so there are really 4 NASA centers that work in entry, descent, and landing, and that's Langley and JPL and Ames Research Center and the Johnson Space Flight Center. Now, we all have different parts. Langley, I would think it's easy to say, we lead the technology development of it. So these new technologies and developing how we are going to put people on the surface of Mars, I think Langley is significantly involved in all the activities that are going on with new EDL technologies. Now there are some, like the mechanically deployable aeroshell, that's being led at Ames, but we're supporting them and helping them with that. And so it really is it's a team effort around the agency. Yeah.
Cost associated with making this dream reality. What are we looking at?
So the question was costs for making this dream a reality, and actually I cannot answer that for the entire human mission, right? And so we're looking at just the technology demonstrations and being able to get there, and then we're working with the architecture folks, which you saw I think the very first week here about the Evolvable Mars campaign and how it leverages activities from across the agency. And so I don't know, Steve, do you have a better answer for that, for what it'll cost?
So, yeah. We've looked at that a lot. And just so you know, I think today NASA gets about $17 to $18 billion a year. Yeah. And the human exploration part of that is 8. With the 8, we do International Space Station, all the work on the station, and we're developing the rocket and the Orion, as well as doing some technology work. And of course, we work for the president at NASA, and the president says we're getting enough. Yeah. However, depending on when you want to get humans to Mars, I think it's safe to say that we may need to spend more at, maybe we're getting about 75 cents on the dollar we need. So we need a marginal increase if we want to actually meet that schedule goal of getting there in the 30s.
Right. Yeah.
It seems like we're littering the surface of Mars with a lot of space junk. Are we concerned about that,
So there's certainly thought given to it. So we have been littering the surface of Mars since the 70s, right? But each vehicle system that we send there goes through these planetary protection, and we make sure that we're not sending, bugs from Earth and germs from Earth and things like that. But yes, some of the vehicle system parts and pieces and the systems that are no longer functional are just sitting there on the surface of Mars now.
Is the debris usable?
Usable in the sense of maybe some future human mission absolutely could use some of the material, but that's not in our plans at this point. We wouldn't want to count on that.
Are the people who are going to walk on the surface of Mars alive today?
So the question is, are the people who are going to walk on the surface of Mars alive today? So we can get people to Mars by the end of the 2030s, right? But given the way government works and how it's most likely going to be the 2040s. So yes, I would say they are. Yes?
Can you just fly to Mars faster than 25,000 miles per hour?
So yeah, that's one of the technology areas that's being worked on. Different types of, I will call them, propulsion to get us to Mars faster. And that, I don't know if they'll talk about that next week, but that's with radiation protection and the exposure during that cruise stage. One of the ways we can mitigate that is actually getting to Mars faster, not taking the 6 to 8 months to get there. And so there's direct propulsive, there's some technology called Vasimer drive and some other things like this that could potentially decrease that time to Mars. And that's really potentially a key for the humans. It's not so much of an issue for the pre-positioning of the cargo missions and things like that. So we can use more efficient and slower methods like solar electric propulsion that would allow us to get there over a longer period of time, but we can also use that to slow ourselves down as much as we can, getting close to Mars, and therefore the landing systems could be more capable when we get there. Yes?
Is the rotational direction of Mars factored in the plan?
Absolutely it is, yeah. So is the rotational direction of Mars factored into the landing? So yes. Well, you can go either way, so retrograde or prograde, but we go with the rotation normally. Yes?
You are relying on radio technology to communicate. What if you change the technology to laser? And if the craft were landing on the side facing the Earth, the device could be in the side of the craft.
Right.
Facing Earth.
Oh, sorry. Yeah. Okay, so the question is,
Communicate during that blackout if you needed to.
okay, exactly. So the question is, why aren't we using laser communication instead of just radio communication to get information back from Mars, from our vehicles? So up to now, we have been using the radio communication. We actually have experiments that are planned to go to Mars to do laser comm. The main thing is, though, to use it during intradescent landing, we have this variable atmosphere to deal with. And so if it's real dusty and issues like that, we don't know that we'd be able to get a good laser signal in those critical times, right? So we still want to have a strong radio signal to a satellite that could then relay it through a laser comm. And so that's why we're looking at laser comm in our orbital assets. And another benefit of the laser communication is it can send a lot more information. I mean, right now, we have a few assets there that communicate through radios, and think of them as pipes. They're relatively narrow pipes that we're sending data through, and there's this big backlog of data and images waiting to go through these pipes. Whereas if we get laser communication working, we'll be able to get a lot more data back.
I'm not sure if the question was about the radio blackout or whether it was about the time delay. If it's about the time delay, the laser and the radio wave travel at the same speed. So there's still, even with laser communication, a 14-minute.
Right. It'd still be the same time delay. Exactly. All right. Thank you all very much.
Thank you for being here, and we look forward to seeing you next week for the last lecture on the radiation protection problem.